Hey everybody, welcome back. This is Math 35, College Algebra at College of the Sequoias. Today we're continuing our exploration of Chapter 1, and today we're dealing with something called complex numbers. This is 1.3, complex numbers. And why should you care about these? This has a lot of real-life applications. Or shows up in real-life applications like alternating current, which is what homes use for what we use for electricity. As well as cellular and wireless technology. If you go far enough down the math hole, the rabbit hole of math, it's connected with anything related to sine and cosine waves. And you'll learn about those in trigonometry and how much they work with the imaginary or the complex numbers. I think we dabble in it in trig, but it comes up a lot later in like differential equations and stuff like that. So that's why it's important. Like most of society is dependent on this form of mathematics. So let's just dive right into it. We have something called the imaginary unit. We use I in mathematics. They use J in physics or electronics. And the reason why they use J is because I is already taken to represent something else. Okay? So we have the imaginary unit I, and it allows us to take the square root now of negative numbers. I is equal to the square root of -1. Back, if we do I times I, equals +1, or -1, sorry, equals -1. That, well, let me put it this way. Square root of -1 squared equals -1. So I is the square root of -1. I squared is -1. And you'll see if we multiply that by I again, we get negative square root of -1, which is -I. And I to the 4th power is I squared, which is +1. So I's rotate between this. We'll explore that more in a little bit. Let's just take a look at where we use them, and we use them. We'll touch on this again later. We'll examine this more later. Top 2 are the most important. I equals the square root of -1, and I squared equals -1. All right. where imaginary units show up are in the complex numbers. So imaginary units show up in complex numbers. And we often like to use the letter Z equals A plus BI. A and B are numbers, real numbers. This is the real part of a complex number. And this part right here is the complex part, or imaginary component. Okay? Complex numbers are also useful for solving when you get to calculus and you're doing integration. You probably, I don't recall doing it in basic calculus, the part I learned, but it can help you solve integrations that are darn near impossible to do with just real numbers. You can take a class on complex number theory that shows you how to do it. Well, we've got I equals the square root of -1. What if it's not -1? It's a value besides 1. But I've got the square root of -3, let's say. This is equal to the square root of -1 times the square root of 3. Remember the rules of radicals we've got. And that first part is I. And that's how we write it. Put the I before the radical. Okay. So if C is just some value, if C is a real number, then the square root of -C equals I times the square root of C. And this rule is the most important rule in complex numbers because breaking it causes the mathematics to break. This rule takes precedence over other rules. Takes priority over other rules involving complex numbers. And you'll see when we get to a spot where you can break the game not following this rule, I'll show you. Okay. Well, actually, let me show you now. It leads to yi squared equals -1. This rule. So this rule leads to yi squared is -1. I squared is I times I And I is the square root of -1 times, and then we got another -1. If we combine them, if we don't turn these to i's first, but instead multiply and combine radicals into 1, we would have something like this. Square root of -1 times square root of -1 equals the square root of -1 times -1 inside the radical. And that would just be the square root of 1, which is 1. But that's not the case. This isn't true. This isn't the correct value. The mathematics work precisely because I squared equals -1. So where this applies in other things, if we have something like the square root of -9 times the square root of -4, the correct way will be treating this as I root 9 times I root 4 by pulling out the negative sign and making it an I. And now you can combine the radicals. We've got I times I, which is I squared. And 9 times 4 is 36. And the square root of 36 is 6. We've got I squared times 6, but I squared equals -1. So that just ends up equaling -6. Square root of -9 times square root of -4 equals -6. That's an example of the way it's used. Don't multiply the radicals together first before creating i's. Before switching the negative to an I. All right. So that's like multiplying them. Let me give you guys one to try. Oh, let's go with let's do square root of -7 times square root of -21. Pause it and try to work it out, and then I'll do it with you. All right, I'll assume you pause it. The first thing we want to do is we want to convert this to i's. So this becomes I root 7 times I root 21. I put the i's together. I times I is I squared. And I can put the radicals together. I'm not going to multiply the 7 times 21 because I think it's easier to do simplifying. If I don't, it's already somewhat factored. Let's factor it a little more. 21 is 7 times 3. So I've got I squared times the square root. 7 times 7 is 7 squared. And I'll put that in its own thing, and I'll multiply that by the remaining square root of 3. And the square root is 7 squared. The square root and the square wipe each other out. They annihilate each other out. We've got I squared times 7 root 3. And now I squared is negative 1. This just ends up being negative 7 square root of 3. All right? That's just multiplying complex numbers and how it works. We'll do some more with that in a little bit. Give you another example. This one involves division. Let's do the square root of negative 42 divided by the square root of negative 3. Well, this is I root 42 divided by I root 3. The i's cancel, and now I've got, and I can put the radicals together. 42 divided by 3 like that under the square root. And 42 divided by 3 is 14. This is the square root of 14. There's no negative number left. The i's cancel each other out. Do another example. Let's do the square root of negative 63 over the square root of 21. I recommend you guys pause it and try this yourself, see what you come up with. All right. I'm going to pull out the I first. And now I can put the radicals together. I'll put the I out front. Let's see, 63 over 21 is, I've got 9 times 7 times is 63. 21 is 3 times 7. 7's cancel. 9 over 3 is just 3. Which means that radical just turns into 3. We got I root 3. Okay? All right, let's kick it up a notch. Do some other things. So let's say we've got something like this. 15 minus the square root of negative 75 over 5. Well, it's a good idea to, I've got two things added together, well, subtracted in the numerator. I can split this fraction up into two fractions, 15 over 5 minus the square root of negative 75 over 5. And this is kind of like the form A plus BI. That's what we're aiming for. Well, 15 over 5, that's easy. Let's just address that now. What's 15 divided by 5? 3. That becomes 3 minus, I'll pull out the negative out of the square root, and I got I square root of 75 over 5. And let's see, 75 is 25 times 3. That's like 3/4, right? Everyone knows money. So I'm going to break up that 75 to 25 times 3, make it 2 radicals, because the square root of 25 is 5. Which means I've got 3 minus I, 5 root 3 over 5. The 5's cancel, leaving behind 1s. And I get 3 minus I root 3. This is the most common way to leave it. To write it because it avoids confusion. If I wanted to make it look like A plus BI, I would put the I at the end. And these are the same value. These are the same. But the first one is easier to read. Okay. And the only purpose really of writing down mathematics, other than for your own benefit later on in taking notes, is like if you're working or doing something like that, you need to share with other people. And so if you're sharing with other people, you should use common notation. Don't reinvent your own mathematics symbols. The plus sign means plus for a specific reason. It doesn't mean something else. All right. Well, that was multiplication and division. We touched on it. We'll do some more with it as we switch to complex numbers. This was just imaginary. This is introduced. Well, this is complex numbers. In the previous page, we just worked at looking at imaginary numbers. Here, we started introducing complex numbers and working with them, manipulating them. And so let's look at more stuff with complex numbers. Operations with complex numbers. We can start off with addition. If I have A plus BI and I add it together with, let's say, C plus DI, well, the A and the C are real components. They'll get put together. And the BI and DI are the imaginary components, and we'll put those together. And we're going to kind of like treat the I like a variable here. We'll factor it out. This becomes B plus D in parentheses times I. And if we look at subtraction, it's similar. I've got A plus BI minus parentheses C plus DI and parentheses. This might be easier to redistribute the negative first. So if I rewrite that, I've got A plus BI plus parentheses negative C minus DI. And then we'll use the same properties we did above. A and negative C are the real components. We'll put them together in one parentheses. And then the imaginary component is the BI and the negative DI. If we factor out the I, it's B minus D times I. Okay? All right. All right, all right, all right. Let's take a look at some examples. I'll do one, then I'll have you do one. Let's go with 4 minus 5i. That's in parentheses, and then we'll subtract -5 plus 8i. I tend to put a little tail on the i's. Put a tail on the i's so that they don't look like a 1. Because a lot of people just write the I or the 1 like that. And if I do that, it may not be clear. It could look like the pen just skipped ink there for a second. That can be mistaken for 1. So if you put a little tail on it, and no, I's or 1s don't have tails on them. All right, so what do we do here? We're gonna, well, let's redistribute that negative, or distribute the, not redistribute, distribute the negative first. If I do that, the 4 minus 5i does not change. Remember, when you're working with this stuff, you should copy down everything that you didn't alter. And if you're working with colored pens or something like that, it also makes it so you can use one color for what didn't change and use a different color for what did change, like I'm doing here. My black ink is for stuff that stayed the same, and the red ink is for what switched. We distribute the negative. Negative and -5 become +5, and negative and +8 become -8i. Now I'll do the grouping together. I'll put my real numbers together. I've got 4 and 5. And plus, and for the complex or the imaginary parts, I've got -5i and -8i. I'll factor out the I, so I've got -5 minus 8 times I. And now we won't leave it in that form. We'll just combine the values. 4 plus 5 is 9. And -5 minus 8 is -13. So I've got 9 minus 13i. All right. I think doing the subtraction one is the easier one to practice because you end up switching it to addition usually anyways. Let me give you guys one. You try. Why don't you do -10 plus 7i minus parentheses 5 minus 3i end parentheses. I'm normally not working this early, and I started recording at 6:30 a.m. because my video game is down for maintenance online. They're upgrading the servers. So started my day off taking care of you guys. All right, I'll assume you paused it, did it. Let's redistribute that, or not read. Let's distribute that -i, or the -1 part. This first part stays the same, -10 plus 7i. And then that minus becomes a plus as I distribute the minus sign. And I've got -1 times 5. Remember, you can put a little 1 in there, so it makes it -1 times them, if that helps. -1 times 5 is -5. And -1 times -3i is +3i. Now we can put together common factors. -10 and -5 are both real numbers. We'll combine those together. And Then we got the plus, we do the imaginary components. I've got 7i plus 3i, which is 7 plus 3 parentheses times I. And when I finish, I get negative 10 plus negative 5 is negative 15. And then I've got 7 plus 3 is plus 10 I. So that's the answer. If I wanted to factor out a common factor, like if I was trying to simplify, let's say there's something in the denominator, like in a fraction. I've got negative 15 plus 10i. 15 and 10 are both factors of 5. Have 5 as a factor. I could factor out the 5 and have negative 3 plus 2i. Well, congestion this morning. So a little nutshell right there, when you're adding or subtracting complex numbers, we want to combine real terms or real components separate from the imaginary components. Okay. All right. That was addition, subtraction, pretty straightforward. It's kind of like what we did when we had variables. If there was an x in there, we can't combine x's with numbers. Just got to treat them separately. So now let's take a look at multiplying complex numbers. Now, I'm sure if you look through the textbook, and maybe they might even, I hope they don't do it in the videos. I didn't look at the videos. We're looking at a plus bi, and maybe we're multiplying it by c plus di, where a, b, c, and d are real numbers. And the book might give you a formula for this operation. It's not worth doing. Don't try to use formulas, just distribute. Don't try to use formulas as they are difficult to memorize and awkward to use. They're really difficult. It's a pain in the butt. So let's just illustrate by example. Let's have 5 plus 3i, and we're going to multiply that quantity by 2 minus 7i. And we'll have FOIL going on. First, outside, inside, last, or basically distributing everything from one binomial to the other. So I've got 5 times 2 is 10. In fact, I'll write it as 5 times 2 real quick. And then I got plus 5 times negative 7i. That's the outside. Then we do the inside, 3i times 2. And then I've got, finally, last, 3i times negative 7i. Now, I wouldn't normally write it like that. I would skip to the next line, but I wanted you to see where everything's come from. I am just distributing, just like we do when we have x's in there and stuff like that. So 5 times 2 is 10. 5 times negative 7i is negative 35i. We just multiply the coefficients, the numerical values. And then I've got 3i times 2. 3 times 2 is 6, so I've got plus 6i. And finally, I've got 3 times negative 7 is negative 21. And I times I is I squared. I can put the i's together real quick. Negative 35i plus 6i is negative 29i. We're just adding the values together. And then I've got minus 21i squared, but recall I squared is negative 1, and I'm going to put that in. So I've got negative 21 times negative 1 becomes positive 21. And now I can add that to the 10, and I get 31 minus 29i. Why don't you guys give it a try? Let's do the quantity 4 minus 5i, and I'm going to square it. And remember, when you're squaring stuff, what do? Especially like a binomial like this, we can't just square each term. You're better off writing it as 2 parentheses multiplied together. That way you'll see you need to distribute. Pause the video, go ahead and take a crack at it. All right, I'll assume you did. If I do this, I've got 4 times 4 is 16. And then 4 times negative 5i is negative 20i. And then I'll do the last term distributed. Negative 5i times 4 is negative 20i also. And negative 5i times negative 5i becomes plus 25i squared. Combining like terms and replacing the I squared with negative 1, I've got 16, 20i minus, or negative 20i and negative 20i make negative 40i. And I squared is negative 1, so 25i squared is negative 25. And finally, when I put them together, 16 minus 25 is negative 5. Or negative 9, I've got negative 9 minus 40i. All right. Next example. This is going to lead to an idea real quick. Let's recall. If I had, let's say, 2 plus the square root of 3 times 2 minus the square root of 3, this is like a plus b times a minus b, which equaled a squared minus b squared. This ends up being 2 squared minus square root of 3 squared, which is 4 minus 3, which equals 1. The radicals went away using conjugates. The same happens with imaginary numbers or complex numbers. If I do 9 minus 8i times 9 plus 8i, I'm not going to use the formula real quick. I'm just going to write it out. 9 times 9 is 81. And then we got 9 times positive 8i is plus 72i. And then I've got negative 8i times 9 is negative 72i. And then negative 8i times positive 8i is negative 64i squared. The i's terms, 72i and negative 72i, cancel themselves out. So I've got 81 minus 64i squared. But I can replace that I squared with negative 1. So I've got 81 minus 64 times negative 1, which becomes 81 plus 64, which is 145. Using the radical version, the radicals went away using the conjugate. Here, the same thing happens. The imaginary values go away when multiplying complex conjugates. When you multiply complex conjugates. And there is a formula. I don't know that the formula helps you any more than it's like the difference of squares one now. But it follows directly from difference of squares. So if I do a plus bi times a minus bi, and I do difference of squares, this is a squared minus bi, that in parentheses squared. But that's a squared minus b squared times I squared. And I squared is negative 1. So this just becomes negative b squared times negative 1 is positive b squared. When we multiply complex conjugates, these are complex conjugates. They have the same values, the same real components, the same complex components or imaginary components, but the sign between them is negative. One's positive, one's negative. We've got a plus bi times a minus bi is equal to a squared plus b squared. I think it's not that helpful. This is a formula. It's a formula. But it's easier to just stick with the difference of squares. To just use difference of squares. And not confuse yourself with similar formulas. And avoid the confusion of similar formulas. And they are similar. Look, up here, I've got a plus b times a minus b is a squared minus b squared. That's our difference of squares. And here I've got a plus bi times a minus bi is now a squared plus b squared. They're similar. One they got the I in the parentheses, and having the I in the parentheses on the b terms makes the end result positive rather than negative. It's easy to mix these up if you try to do that. It's easier just to stick with the difference of squares and recall that I squared equals negative 1. You need to know that anyways. No point coming up with a third formula. And the very idea, since complex conjugates, when they multiply together, pause this if you need this up longer. since complex conjugates, or the multiplication of complex conjugates, removes the imaginary component, this is how we will deal with division. Of complex numbers. And this is exactly what we did with radicals. Exactly what we did with radicals. Which is good because I is technically a radical. It's the square root of -1. We don't leave radicals in the denominator. We multiply by the conjugate. So let's just take a look at an example. I'm going to start off with 5 minus 5i, and we're going to divide that by 3 plus I. Okay, that's where our example starts. I've got a complex number on the bottom. Since I do, I'm going to want to multiply by the conjugate of the bottom on top and bottom. The conjugate of the bottom, we just change the plus sign to a minus sign. So 3 minus I and 3 minus I. Now, since I've got plus signs and minus signs in there, addition and subtraction, I should introduce parentheses to make it clear that I need to distribute. So on the top, I've got 5 times 3 is 15. 5 times negative I is minus 5i. And then I've got negative 5i times 3 is minus 15i. And then negative 5i times negative I is plus 5i squared. I'll use the difference of squares formula on the denominator. So a equals 3 and b equals I. I've got a squared minus b squared is 3 squared minus I squared. So, well, let's combine like terms and make that I squared a -1. So on top, I have 15, and then negative 5i minus 15i is negative 20i. And I'm going to write that I squared as -1. So 5 times -1, that's the top. On bottom, 3 squared is 9. And I squared was -1. So I've got 9 minus -1. So this is 15. 5 times -1 is -5. So I've got 15 minus 5 is 10 and minus 20i. On bottom, I've got 9 minus -1 is positive 10. And the top, I can factor out the 10, or you can separate it. This is just two approaches here. Option A, I'll show both ways in case you like one way over the other. I can turn that into 10 over 10 minus 20 over 10i by splitting up fractions. 10 divided by 10 is just 1 though, and 20 divided by 10 is 2. I get 1 minus 2i. So splitting it up as fractions is one way of dealing with that. And then if it doesn't completely cancel with the denominator, this is actually the better approach. Because the denominator does not always completely cancel. But it is helpful to practice your other math skills because they're helpful. I could also factor a 10 out of the top, and I get 1 minus 2i over 10. And now I've got 10 on top and bottom. They cancel, and I'm left with 1 minus 2i again. So both skills are good. The first one, splitting them into two fractions, is more useful in the long run, but you should be comfortable with being able to factor stuff out and cancel. Which is a lot more useful in other things, but it is a math skill. Now, notice if the denominator doesn't have a radical, or is just imaginary. What if the denominator is just imaginary? I've got, let's say, 15 over negative I. Well, the real component here, this is like 0 minus I. So the conjugate would be 0 plus I, and I don't need the 0. So what I'm really just going to multiply by is I over I. Okay? Which gives me 15i on top and negative I squared on bottom. But I squared is negative 1. So I've got negative, negative 1. Negative, negative 1 becomes positive 1, and this just becomes 15i. Okay? So I'm going to go back to looking at those powers of I. I touched on them at the beginning. Powers of I, or exponents of I. So I could start off with I to the first. That's just I. So I'm going to make a list on the right, and I'm going to show the operations on the left. If I do I squared, this is I times I. Which just gives me negative 1. We talked about that earlier. If I look at I cubed, it's I times I times I. 2 of the i's make up a negative 1. This is negative 1 times I. It's just negative I. So I cubed is negative I. I to the 4th power is I squared times I squared. I could write it out as the individual i's, but I squared I have a value for is negative 1. Negative 1 times negative 1 is positive 1. So I to the 4th value is plus 1. If I do I to the 5th, this is I to the 4th times I. And I to the 4th is just 1. So I've got 1 times I, which is just I. And you'll start to see a pattern here. I to the 6th power, I could do as I to the 4th power times I squared. I to the 4th power is positive 1, I squared is negative 1. And multiplying those together gets me negative 1. So I to the 6th power is negative 1. I to the 7th power, I to the 4th power times I cubed. This is positive 1 times negative I. I'm just pulling these values from up here, from I to the 1st to I to the 4th. This just gets me negative I. So I to the 7th equals negative I. And if I do I to the 8th, this is I to the 4th times I to the 4th. Both of those are just positive 1. And 1 times 1 is 1. I to the 8th equals positive 1. Notice this is cyclical. Exponents of I make a cycle. I, negative 1, negative I, 1. It's a cycle that repeats itself, and notice it's every 4 powers of I. Every 4 powers of I. Which allows us to shortcut stuff. I'll give you an example. We can use this property to our advantage. Let's say we've got I to the 17th power. Just keep pulling out factors of 4 or multiples of 4 out of that 17. So I got I to the 4th times I to the 4th. That would be 8. Another 4. 4 plus 4 is 12. Add another 4 would be 16. And then I need one more I. And all of these are just 1. 1 times 1 times 1 times 1, except the last one, which is I to the 1st power. So I to the 17th is just I. The easiest way to do this is divide the exponent by 4. And your remainder is the simplified exponent on I. So if I did that here, 17, I'll divide 17 by 4. 4 goes into 17 4 times. 4 times 4 is 16. We subtract, I got 1. That's my exponent. And notice that's what I had right there, I to the 1st power. How does that help us? Well, what if I had like I to the 99th power? Do I really want to break out I's 99 in sections of 4 till I get to 99? No. Let's do 4 into 99. That goes in twice. 2 times 4 is 8. I'll subtract, I get 1. I'll bring down the 9. 4 goes into 19 4 times. 4 times 4 is 16. 19 minus 16 is 3. That's the only thing that matters. I don't need the 24. I just need the 3. This simplifies down to I cubed. And I cubed was negative I. So I to the 99th power is negative I. We could do something similar if we had negative exponents. If I had like I to the negative 14th power, this is 1 over I to the 14th power. Do the same thing, 4 into 14 goes in 3 times. 3 times 4 is 12. We subtract, I get 2. This is 1 over I squared, which is like I to the negative 2, but I wouldn't leave it as I to the negative 2. I squared is just negative 1. So 1 over negative 1 is negative 1. Okay, that wraps up 1.3. And what are we doing next? 1.4 is on, let's see, let me take a look at it. 1.4 is on quadratic equations in one variable. We're going to start looking at x squared equations and solving those. And the reason why we hit on complex numbers first is because some solutions to quadratic equations are complex. All right? Peace. Stop recording and have a good day, everyone.